Unit Operation Classroom, an initiative of unitoperation.com. We are discussing now GATE 2024, question 63. Consider the search drum in the figure. So this is our search drum here. Initially, the system is at steady state with a hold-up volume of V over 5 meter cube. So here, so this is operating at steady state. What's the flow coming in and the flow going out? And the volume and the hold-up volume here is 5 meter cube. That is at steady state, which is 50% of the full tank capacity. So the full tank capacity, of course, is going to be 10 meter cube. So that the full tank capacity is, of course, 10 meter cube. The high, okay, and the volumetric flow rates are 1 meter cube per hour. So at steady state, this is 1 meter cube per hour. This is going out at 1 meter cube per hour, and this is 5 meter cube. And there is, of course, a level transmitter here, and that gives a level controller, and that feeds this control valve here. And this is operating at steady state, and this is 1 meter cube per hour, and this is also 1 meter cube per hour at steady state, and this is at 5 meter cube. And as we said, the total volume of this one is 10 meter cube, we full. The high hold up alarm is, of course, if it goes to 0.8 times of the full capacity right here, which is, of course, going to be 8 meter cube, or the low alarm is given at 20% of the full capacity, which is at 2 meter cube. So this is my 2 meter cube, and that will give a low alarm. And this is at 8 meter cube. This is a high alarm. And when this reaches these two different alarm positions, and of course, there will be necessary actions will be taken for the proper controlling of the liquid level. A proportional controller manipulates the outflow to regulate the flow, F out. So let's say V is at any time T, the hold up volume is V. It could be here, it could be here, anywhere. So the difference between the hold up volume at any time t and the steady state, and of course that's multiplied the proportional gain here, and f out of standard, the f out is the steady state value, which is 1 meter cube per hour. So corresponding the f out would be is this value would be calculated. So this flow of volume would be changed accordingly according to the level in the instantaneous level of liquid in this particular search drum. Assume at time t is equal to 0, f increases from 1 meter cube per hour to 2 meter cube per hour. So this is operating at steady state 1 meter cube per hour. Suddenly there is a step input and a step change in the input flow rate, and that is a 2 meter. So that's a 2 meter cube per hour. Okay. Um, Let's quickly see what is an application of this one. So this is a very good application in terms of, let's say, distillation column. Say this is in a distillation column. This is over the vapor line, and this, of course, is a reflux drum, and this feed rate. So this here, the level level it may change, change in the reflux drum, which is this drum right here, the surge term right here, may fluctuate due to fluctuation in the upstream heater or the desalter. So upstream, in the feed flow rate, whatever is coming in according to the changes here, the heater disturbances or the desalter disturbances, the corresponding the vapor flow rate here and the corresponding level in the surge drum may change. If there's a high level, there will be liquid carryover, which is dangerous. And at the low level, of course, there will be a vapor breakthrough through the surge drum, which will lead to column instability. So, of definitely before it reaches the high value or the low value, appropriate control action should be taken, which is done according to this one. So the question is, let Kese minimum be the minimum controller gain that ensures we never exceeds V high. So we have to find out the value of Kese minimum. So this is a very standard problem. Okay, let's do the dynamic balance. Let's say V is the holder firm at any time t, it could be anywhere, and that's equal to F in minus FF. Standard mass balance, and since density is constant, is a volume balance here. And F in is of course is equal to 2, and F out we have seen that is equal to this one right here. So, and F out, if this is at steady state, that's equal to 1 meter cube per hour, right? So we put that here, and the corresponding value is this one right here. Now let us define the deviation variable, and it's a small v, which is at any the holder volume at any time t, instantaneous value minus the steady state value, which is of course equal to v minus 5. This is the steady state value, 5 meter cube. Okay. So if that is so, then this dv over dt, of course, is dv. This is going to be equal to d of dt of v minus 5. So that's of course is going to be equal to small dv over dt, right? Which is this one right here is equal to 1 minus kc into v. So this is equal to small v. And if we do the integration, this is a very simple and standard integration. It's shown in detail in this website here. So we get that. Okay. So Vt, since V is equal to, capital V, that is a holder volume at any time V, it's going to be equal to V is going to equal V plus 5, right, by this definition. So Vt at any time t is of course given by this expression right here. Okay. And of course, we can see at the time t is equal to infinity, so the V max is going to be equal to 5 plus Kc. So this would be equal to 0, and this is equal to 5 plus Kc here, right? So that is V max. So to ensure that the V max is always less than, V max is always less than the V high, which is 8 meter cube, we can write 5 plus Kc. This should be always less than this, and which you do the calculation, it will be Kc should be always greater than equal to 3. So the minimum value of Kc should be equal to at least small, the value of Kc should be equal to 1/3. That's equal to 0.33 our inverse. So that is the answer. So that value of Kc should be set here, so that the V max never reaches. So V max is always at or below this V high value, so that any disastrous effect, like let's say in case of any upstream changes, this level never goes exceeds this value of high level in the search term. So as I said, the answer is this one. Kc minimum is 0.33 our inverse. So this is the answer.